Hi, this is A Plus going over the sample practice questions for Unit 8, which is about acids and bases. We'll start off with conjugate Bronsted-Lowry acids and bases. So if we start looking at question number 1, question number 1 has two waters. These two waters can either be taken as an acid or a base. So if we look at the first one here, that's if we take that one as just the acid, from the definition we know the acid loses a proton. So if this is the acid, we can see that one of the products has one less hydrogen ion. So if we go across to see which product it is, it's got to be this one here. Therefore, this one's got to be our conjugate base. We therefore know that the next one's going to be our base, and that one's gained a proton, so it's going to be our conjugate acid. Looking at question number 2, we've got our acid, which is sulfuric acid, so we know that's our acid. The hydroxide is our base. So we look at the acid must have lost a proton. So which one of these two has lost? It's HSO4-, which is our conjugate base, and therefore it's easy then to identify our actual base, which is the hydroxide, and then the conjugate acid, because hydroxide has gained the hydrogen. If we look at number 3, we've got sulfuric acid again. So if we look at sulfuric acid is the one which has lost the proton. So this is our acid. We look to see which product has lost the hydrogen from the sulfuric acid. It's this one here. So it's going to be our conjugate base. Remember, the acids always form the conjugate bases, and the bases will form the conjugate acid. So this one here, which is water, must have gained the proton to give us a conjugate acid. We look at question number 4 in a similar way. We've got acid and base. Well, in this case, it's easier to identify the base. Here, this is the hydroxide. This is our base. So this must have gained the proton. So if we add a proton of this, we're going to end up with water. So we've got two waters. So we can take the first one as being our conjugate acid, which means the acid was the hydronium ion, and it forms a conjugate base because it lost the proton. And number 5, if we look at question number 5, we have the weak base, which is ammonia. So this must have gained a proton. So we look at the product. The only one which seems to have gained a proton is this one here. So this must have been formed from the base. So this is a conjugate acid, and water is our acid, so it must have lost the proton. So if we lose one proton, it's going to form this one here. This is going to be our conjugate base. Looking at the next set of questions, which is about naming acids and bases, if we look at question number 1, we can see that we have a nitric acid. The important thing here is to make sure we understand that anything which has the polyatomic ion, so we've got question 1, 3, 4, 5, 7, 8, and 10. All these have polyatomic ions. So the polyatomic ions are going to end up with the name of the acid simply from knowing the polyatomic ion. So the first one is nitrate. So we know we have nitrate. So that's going to be end up with nitric acid. They're going to have an IC ending. It does not have hydro. Hydro is only for the ones which are not polyatomic. So for example, here we have the chloride. The chloride will change to chloric, and it will have the starting term of hydro. So number 2 is going to be hydrochloric. Number 3 is the sulfate. So sulfate will be sulfuric acid. Number 4, it's not the sulfate, but it's very similar, SO3. So SO3 is the sulfite. The sulfite will end up with the sulfurous ending, and with sulfurous acid. Number 5 is the acetate ion. So the acetate will be a polyatomic, so that's going to end in acetic acid. Number 6 is just the bromide. It is not polyatomic, so that's going to start off with hydro. So it's going to be hydrobromic. The "ide" changes to an "ic." And number 7 is a polyatomic, so it's a nitrite. Nitrite will have an ending of "us", so it'll be nitrous acid. Number 8, phosphate, again polyatomic, so we don't have a hydro, it'll just end in an "ic", so it's going to be phosphoric acid. Number 9 has no polyatomic, it's just sulfide ion, so that's going to be starting with hydro, so hydrosulfuric. And number 10 is a carbonate. The carbonate is going to change to an "ic", so we're going to end up with an "ic", and that's going to be our carbonic acid. Okay, let's look at the next set of questions. This is about neutralization. Neutralization is acid plus base gives you salt and water. So these are sort of questions we should know, that we end up with water for each and every one of these equations. So we need to make sure we can use our stoichiometry balance at the end. I'm going to go through it, try and find out the names of the products. So here we have the sulfuric acid and potassium hydroxide. So the potassium is going to take the place of the hydrogen, and you're going to get potassium sulfate and water. And then we can just go ahead and balance from our stoichiometry knowledge. If we look at the second question, we have the phosphate and we have lithium. Now remember your reactivity series, lithium is more reactive than hydrogen, so it's going to take its place. So in this case, we can predict our product as being lithium phosphate and water. Number 3, we have carbonic acid and we have magnesium. So again, magnesium is more reactive than hydrogen. It's going to take the place of the hydrogen to form magnesium carbonate. So this is our carbonate here. So we can see we end up with magnesium carbonate. The next one, again, we have acetic acid and we have sodium hydroxide. So the sodium is going to take place of the hydrogen, is going to combine with the acetate. So we're going to end up with sodium acetate and water. And number 5, we're going to look at this again, and we have calcium hydroxide. Calcium is more reactive than the hydrogen, so it's going to join up with nitrate. So in this case, we're going to end up with our answer as being calcium nitrate. Now remember, really in aqueous solutions, they don't really combine together as such unless they are insoluble and form a precipitate. Now we'll look at the next question, which is all to do with pH and pOH. Now when we do these questions, we need to make sure that we understand all the formulas on the page here. So number 1, number 2, 3, 4, and 5 up on the side in green, so you can see all those. And we need to understand what the question is asking. It's asking us to find out the hydrogen ion concentration, and we know the pH. Okay, so let's look at our formulas, see which ones we need. So if we look down, we'll see the hydrogen ion is number 4. So we've got to calculate the 10 to the power of the negative pH. So if we do the 10 to the power of negative pH, we'll end up with the correct answer. So it's looking at and knowing your formulas to use. Number 2 is what is the pH of the solution. So we need to find out the pH of the solution, and we've got to try and find out, well, how do you know this? Well, we know the pH, and we need to find out the we need to find out the pH from the OH concentration. So from the OH concentration, we need to try and work out what the pH is. So first of all, we need to find out the pOH. So looking at this question, we have to look at the concentration of OH, and we use formula number 2 to find the pOH. So we need to do number 2 first, and then from number 2 we use number 3 to work out the pH by 14 minus pOH. So we'll be able to find out the pH by using numbers 2 and 3 on our formulas on the side. So just be careful with that one. We've got to look at two different formulas to get to the answer. If we now start looking at the next question, our next question is number 3. Number 3 is asking us to find out the hydrogen ion concentration from the POH. So in this case, what we're going to do, we're going to find out from the POH. We're going to look at number 3. So we can find out the pH from this equation. So we're going to find out we have POH, so it's going to be 14 minus POH. Once we get that, we'll be left with the pH. Once we have the pH, we then have to try and find out the hydrogen ion concentration. So we're going to look at formula number 4 and perform that calculation by doing 10 to the power of negative pH, and that will give us our answer here. Now if we look at the other question underneath, which is looking at the identifying the species, well, if we look at the species, we'll be able to see that the first one is HCl. So we look at HCl, and all we have to do is know that it's strong acid, so it's going to break up. It's going to break up into H plus and Cl minus. So that's what we need to look at, and there we have the answer of H plus and Cl minus. Now if we look at the next one underneath, we have NH4 plus. Well, NH4 plus is again an acid, so it's going to lose one of the hydrogens. If it loses one of the hydrogens, it's going to form NH3, which is ammonia, and be left with the acid. Okay, so remember all these are acids, so they've got to produce the H plus ions in the first place. So whatever you do, read the question and it'll give you a big clue. So in this case we have HCl3 1 minus, so if we remove the hydrogen from there, we will be left with the CO3 2 minus, so the H plus is important first, so we have that, and then we have the CO3 2 minus. If we now look at question number 2, question number 2 is asking us to calculate the pH to 2 decimal places. Now you have to use your calculator to make sure you get it correct to the 2 decimal places. I'm about to show you how to work through this problem so we can see. So we need to work out the pH. Again, we have a strong acid, so that strong acid is going to tell us that it's going to dissociate completely. So if we know the concentration is 0.25, we know the hydrogen ion concentration is also going to be 0.25 because it dissociates completely. HCl will go completely to H plus Cl minus. Therefore, if we know it's a 1-to-1 ratio, we know the hydrogen ion concentration, and we simply use pH is equal to negative log 10 of hydrogen ion concentration, and that will give us the answer of 0.6. In a similar way, if we start looking at the next question is looking at 0.5 molar nitric acid, and again nitric acid is a strong acid, so it's going to dissociate, and it's a 1-to-1 with similar to the HCl, so we again will know the concentration of hydrogen ion, so HNO3 goes to H plus NO3 minus. So we've got 1-to-1, and again 0.5 we know is the concentration of hydrogen ions, and then we simply then plug it in to pH is equal to the negative log 10, and we'll get the answer of 0.3. Hi, this is A Plus with part 2 of the acids and bases questions. We're going to look at number 3 of the pH calculations. Question 3 is asking you to calculate the pH to 2 decimal places and taking into account Kw of water. Well, Kw is the concentration of the hydrogen ions multiplied by the hydroxide ions by looking at the green equation formula. 1, and number 2 is pH is equal to the negative log of the hydrogen ion concentration, like we looked at before. So we look at part A. The question is asking 0.15 sodium hydroxide, and it's asking to calculate the pH. Well, we know the hydroxide ion concentration, so if we think about what we already know, then it's going to be looking at the concentration of the sodium hydroxide, which tells us the hydroxide ion concentrations, which is going to be exactly the same. So we know exactly what the hydroxide ions are going to be. From there we can use formula number 1, and it's going to be 1 times 10 to the negative 14 multiplied by 1 times 10 to the negative 14 equals the hydrogen ion concentration multiplied by the hydroxide. Now we already just said the hydroxide was 0.150. From here we can do a little bit of math and just calculate the H plus. So it's going to be 1 times 10 to the negative 14 divided by 0.15, which will give us the hydrogen ion concentration. Once we know the hydrogen ion concentration, we can use formula number 2. pH is equal to the negative log. And when we do the negative log, we'll be able to work out the answer is 13.18. Similarly to the first part, we've got 0.26 moles of magnesium hydroxide. The magnesium hydroxide has got 2 hydroxide ions in there. So for every 1 molecule of MgOH2, we get 2 OH minuses. That's just to remember what the question is asking us to do. So we need to find out the pH. So again, from here we can work out the hydroxide ions are going to be 0.261, which was the concentration of the magnesium hydroxide, but we've got to multiply by 2, because if you look at the stoichiometry, we said there were 2 hydroxide ions for every magnesium hydroxide, which gives us the 0.522. We can then continue to use the same formula, formula number 1, and we can work out our hydrogen ion concentration, which is this value here, 1.92 times 10 to the negative 14. And then we use the pH equals negative log of the hydrogen ion concentration, and that will give us our pH of the solution. Now if we look at question number 4, it says calculate the concentration of the following basic solutions. So we need to look at the basic solutions. It's given the value of Kw, so we know Kw is equal to hydrogen plus hydrogen ions multiplied by hydroxide ions. So if we look at A is saying KOH, pH is 11. So we need to work out the concentration of KOH. So if we start looking at the concentration of KOH as a thing that we want to find out, we know that we have the pH of 11. So once you know the pH 11, we can work out the hydrogen ion concentration, because we know the hydrogen ion concentration is the negative log of the hydrogen ion concentration, so that the pH is equal to the negative log of the hydrogen ion concentration, and hydrogen ions is equal to 10 to the negative pH. So from here we can work out the hydrogen ion concentration by doing this calculation, and we get a value of 1 times 10 to the negative 11. So that's hydrogen ion concentration. Once we know the hydrogen ion concentration, we can use equation number 1, which is in the green on the right hand side, and from there, by doing simple math, we can work out the concentration of the hydroxide ion by dividing Kw with the hydrogen ion concentration. We will then have the answer for the hydroxide ion concentration. Because KOH produces 1 hydroxide ion, it's one-to-one relationship, so therefore the answer is going to be the same for the KOH concentration. Whereas question number 2 is slightly different. We're going to look at this. The calcium hydroxide gives us 2 moles of hydroxide ions. So each one of the COH2 will give us 2 moles of hydroxide ions. And again, we have a pH given to us. So if we know the pH, again, we can work out the hydrogen ions by using the formula given, and we'll end up with this answer here. Once we know the hydrogen ion concentration, again using equation 1, Kw is equal to hydrogen ions multiplied by hydroxide ions, we can work out also the value of the hydroxide ions. So the hydroxide ions over here will be 2.82. Once we know that, we know also that 2 hydroxide ions. If we know that that's 2, our ratio is going to be 1/2 in order to find out the concentration of this. In other words, once we find out this, we just have to divide it by 2 to get our final answer here. Now, if we look at the acid-base titration question, we can see that there are various graphs, the S-curves for the titrations, and tells us that certain amounts of titrate are added, 25 cubic centimeters, and there are 4 titrations, and the base concentration is given, and we need to choose the correct titration curve, name a suitable indicator for the titration, and for titration 1 and 2, we need to calculate the concentration, and they've given us the concentration of sodium hydroxide and the volume for number 1, and similarly for the other ones we need to calculate for, and the acids used for each one. So if we just quickly just look at the concentrations and values and the data table given to us, we will be able to see that we have here strong acid, weak acid, strong acid, weak acid. So we can already make those strong, weak, and if we go across, we can see that this one is going to be weak base. The one directly above is also going to be a weak base. This is going to be a strong base because it's hydroxide, potassium hydroxide, and this is going to be strong. So we can see strong, 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 weak, weak, strong, weak, weak, and that'll help us label all the graphs together. So what we're going to do, we'll go down to the actual solutions to each one of these and we'll talk through them. So if we look at the first one here, we can see that that is number 1. That's going to be strong, strong. So we can see easily that that was a strong, strong. So we labeled it 1. That was the one that we needed from our table given to us. So we can see that's strong and strong. And similarly for the other one, it's going to be here. That's sort of like weak, and that's going to be strong acid. And we need to make sure we just look over our indicators to select the right ones. For this first one that we have over here, it's going to be phenolphthalein or methyl orange. You could pick any one of these two to fall into the range where the vertical line is. So for each one we need to look at the vertical part and see what the range values are here, and we select a sensible one for that, and that's going to be phenolphthalein. For the next one, across from it that we need to look at is straight part here. Again, that's not going up to 10, so in this case it's going to be methyl orange is the one that we'll select. And if we continue looking at the question underneath, we'll be able to see the calculation for that part. We know we have been given sodium hydroxide and hydrochloric acid, so we simply write out the equation. So we know we're going to get salt and water, so we know exactly what's going on. We know the volume, and we know the concentration, so we can work out the moles. Number of moles is molarity times volume, so we can work that out from your stoichiometry. So we can find out the value there. And the volume needed for neutralization is 14. So that's given to us again. So we know that's going to be 14. So we use, some of you may use M1V1 equals M2V2 to work this out. You can do it that way if you so wish. So you can work out the unknown quantity from there, and you'll get your answer of 0.18 moles. If not, you can just continue to work out the number of moles you have for sodium hydroxide, and if you look at the concentration of the hydrochloric acid we have over here, it's going to be number of moles of sodium hydroxide, which is going to be the same because the moles are the same in neutralization when they neutralize each other, divided by the volume of the acid, and that will give us the answer of 0.18 moles. And just to finish off this question, if we look at the other two graphs, we have this one being classified as being number 2 because it is a weak acid, and we have a strong base right at the top here where it's 14, so you can see that's a strong base. And the one next to it is going to be weak and weak. We can see the difference. pH is just approximately 9, and the pH at the end is around about 3. So we know that's going to be classified as being number 4. So we will now know how to classify those two. With this one, it's difficult to select an indicator because there's not much of a vertical line, and therefore indicators are not going to be too great with that type of a reaction. If we look at the one next to it again, coming back to the one that we circled, number 2, we can see that number 2 is going to be the one that's going to be, we'll use phenolphthalein for that one because it goes right up to 14, so we can use phenolphthalein as the indicator. The calculation is going to be pretty simple. Again, we know the reaction, we know the moles of KOH, so volume times concentration is going to give us the value of 2.5 times 10⁻³ and the volume of acetic acid needed to neutralize is going to be 42 cubic centimeters. So again, the concentration is going to be, for the acetic acid, is going to be equal to 2.5 divided by the volume, and it will give us 0.06 for that answer. Hi, this is A+. We are looking at the buffers questions. So let's continue with the first buffer question. It says Mark and Karen are carrying out a science project on the application of buffer solutions in the human body. They have discovered that a buffer of carbonic acid H2CO3 and hydrogen carbonate HCl3 is present in blood plasma to maintain a pH of between 7.35 and 7.45. Why do you think buffer solutions are needed in the body? Well, in your notes you have discovered what buffers are. They sort of maintain the pH value. So part A is worth 2 questions. So let's try and give 2 possible sensible answers. So if we start looking at the answer itself, it says on the addition of H+. Now H+ here means if you add acid. So if you're adding acid, you're adding hydrogen ions. And if you've done any work on Le Chatelier's principle, that equation is going to shift one way or the other. So when you add hydrogen ions, the equilibrium will shift to the left. That means it will try and reduce the amount of H plus ions present. So it will go back to the acid form. So it will remove all the hydrogen ions and it will try and maintain the pH that was there presently. That's a very straightforward, simple answer. Part 2, the second point, is really looking at how the equilibrium changes when you add the hydroxide ions. So if they are hydroxide ions added, so if we're looking at part 2 here, if there's an addition of hydroxide ions, then the hydroxide ions are going to react with the excess acid to produce water molecules. And when that happens, it's going to get rid of the hydroxide ions that were added. And so by getting rid of the ones which are added, it's maintaining the pH by producing water. So that was the answer to the Bufford's question, part 1 and 2. Okay, if we now start looking at question number 2, which is another Bufford question. So the Bufford solution is a solution that resists a change in pH when a small quantity of acid or base is added. So if we look at part 2a, it says a Bufford solution is made by mixing 0.510 moles of methanoic acid and 0.45 moles of sodium methanoate. We should recognize that we have the methanoate, which is the conjugate of the methanoic acid, which means we have a Bufford solution. Now we have specific amounts here. We have 0.510 of methanoic acid and 0.45 moles of sodium methanoate. It's the methanoate ion which is important. So what is going on? Part 1 asks us to look at the question, and it's asking us for an equation. So what is the equation actually representing here? Well, if we look at the starting point, we have methanoic acid. This is our formula for methanoic acid. Methanoic acid is 1 carbon, and the organic formula would be something like this. And the H is here. And it's this hydrogen here which gets lost when it dissociates partially. So if we think about this hydrogen being lost, we'll be left with the HCOO, or HCOO, which is this bit here. So we're left with that methanoate ion and the hydrogen ion. So that was part 1 of the question. Part 2 is asking us to calculate the pH of the buffer, and it's given us the pKa, and the pKa is 3.75. So if we approach this again in a similar way to what we have with the previous acid-base questions, and we can see that pKa means the negative log 10, like we had pH. So pKa is like pH. The P is negative log 10, and then our Ka. So if we wanted to just find out Ka from here, we can do it to 10 to the power of the negative pKa, which gives us the Ka value of 1.78 times 10 to the negative 4. And if you have done this in class where you've looked at what Ka means, the dissociation constant, it's going to be the products, the concentration of the products. If you look at the equation above, it's going to be the concentration of the HCOO minus ions multiplied by the hydrogen ions divided by the concentration of the acid. So really, when you're looking at that here, we should be thinking about really products over reactants. So that should be what we do. Once we have done that, in order to find the concentration, well, concentration is number of moles per liter. So that's our definition of number of moles. So, concentration. So if we find the concentration of the methanoate ions, we know we had 0.45 moles. If we divide it by the volume, we'll get the concentration. Similarly, if we do the same with the acid, we had 0.510 moles and we had a volume of 0.5 liters. Now, decimeter cubed is the same as liters. So don't worry about that too much. As long as we either use dm to the minus dm cubed, which still means liters, you'll get your answer moles per liter. So now you've got your two values of moles. And then if you substitute these values in, we will get 1.78 times 10 to the negative 4, that's our Ka, is equal to 0.9 multiplied by the hydrogen ion concentration. So the only thing we didn't have was if we substitute this back into our equation here, we have Ka, we have the concentration of the acetate, we have the concentration of the acid, and the only thing we do not have or need to find out is the hydrogen concentration. So if we continue with our mathematical calculations, you should, just by manipulation of that formula, end up with 2.02 times 10 to the negative 4 moles per liter. So if you know what the hydrogen ion concentration is, if you want to find out pH, you do the negative log of the hydrogen ion concentration. And then if we continue looking at the next question, which is part B, if we just go to part B is asking us to look at or explain how this buffer resists change in pH on addition of small quantities of acid and bases. And again, it's very similar to the previous answer we've given to one of the other questions. So on addition of hydrogen ions, we need to then look at which way the reaction will go. So if you add hydrogen ions, it's got to shift in such a way that it will remove those hydrogen ions, okay, and therefore maintain the pH. So that's the important thing with this question here. That explain how this buffer resists pH changes. Well, if you add hydrogen ions, you are decreasing the pH. So if you remove those hydrogen ions, you are making it go back up to what it was previously or very close to it. And similarly, if you look at part 2, it says what happens if you add a small amount of base to this. So if we look at this, the base is going to be adding OH minus ions. So if you add OH minus ions, you need to try and get rid of them. So what the acid does is it will react with the excess or the addition OH minuses, and it will form water molecules. So when it forms the water molecules, it's actually getting rid of this ion here, therefore maintaining the pH once again. So those are your solutions to the problems. It's always good practice to look over and check your notes prior to working out the problems and learning the formula, so it makes it easier for you to do the calculations. Thank you.